Welcome everyone to this question. We have a rod which is connected to a disk like this. Now this whole system is going inside a curved surface. That bigger curved surface I'm drawing here. This is the curved surface in which the whole system is moving. So our question again has two parts. There is a point A in the system somewhere here. We are given that what is the velocity, angular velocity of the rod, omega. That is given to us. So obviously the system is going against gravity. So after some time, uh, uh, moving with the in this vertical circle, it will reach the highest point. So basically, we are given also that what is the length of the rod. Let's say that is some L, and what is the radius of this disk. That is given R. Question is find what is the velocity of point A. And second part, write the equation to determine what value of angular velocity is required at the current state so that the whole system is just able to reach the uh, highest point of motion. That is this vertical line. It is able to reach. For that, what would be the value of omega? So to find that value of omega, we would need an equation. So you have to write that equation. So let us begin. So first of all, we will be beginning by writing what is the velocity of point A. So uh, first of all, we have to decide how the disk is moving. So the disk is moving in this direction, would moving in the opposite sense as that the rod. So whatever the angular velocity of the rod is, it will provide the velocity omega L to the center of the disk. So this is velocity of center of mass of the disk, VCM. We know that for rolling, the omega dash r or the velocity of the peripheral point of the disk should be equal to VCM. So this gives us a simple equation that omega dash r is equal to omega L, or omega dash is equal to omega into L by R. Uh, then what is the velocity of highest point? That is point, not at the highest point, but of point A. It is the highest point at for this disk. So just the direction we have to evaluate. Point A, its velocity is going to be in this direction towards rightwards. It would be omega dash r to the right, and vertical direction would be simply omega L. So velocity of point A would be omega dash r I cap plus omega L j cap. So thankfully both the values are available for us, and they are equal as well. So we can simply write this as omega L I cap plus j cap. So in the original question, it was given that the value of L is some 120 mm and omega is some 10 radians per second. So if you substitute those values here, we can find velocity of point A. Now moving on to second part. So for second part of the question, we need what is the rod. So rod is of mass small m. Let's say this is the rod's mass and the disk's mass is capital M for the disk. So we'll apply conservation of energy here. Conservation of energy says that the initial energy of the rod, that is half ml square by 3 into omega square. This is the rotation kinetic energy of the rod initially, plus the rotational kinetic energy of the disk, that is half capital M r square by 2 omega dash squared, plus half translational kinetic energy of the disk, that is simply half m vcm square. This will be equal to the gain in the gain in gravitational potential energy of the whole system. So there we have to be careful. The center of mass of the rod is going to rise by height uh, L by 2. So there we are going to write mgl by 2, and the disk itself is going to rise by a height of L. It's going to go with this rod at the topmost point of the rod. So it's going to rise by L height. So we will write mgl. This is the gain in potential energy, and this whole term is loss in kinetic energy. At the highest point, we do not need any kinetic energy of the rod. Kinetic energy not required. Just it should be able to reach that particular point. And here we will substitute whatever value of omega dash we have, that is omega L by R. Substituting omega dash is equal to as omega L by R. Substituting that value, we will get whatever value of omega which is required for the system to reach the highest point. So that's it for this one. I hope it was clear. So thank you for joining and have a good day.